Hi, welcome back to General Chemistry 1. Today we're going to talk about Hess's law. This is the last topic in chapter 6, and it's very important because it helps us to do a lot of calculations. So what is Hess's law? It says the enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. In other words, the enthalpy change of the overall reaction equals to the enthalpy change of the step 1 plus enthalpy change of the step 2, step 3, and etc. Okay, that means if we don't know the enthalpy change of the overall reaction, but we know the enthalpy change of individual steps, then we can use Hess's law to find enthalpy change of any reactions, of that overall reaction and also any reactions. Okay. For example, if we want to know the enthalpy change of this reaction, 2 carbon solid plus 2 water in the gas phase to produce 1 methane in gas phase and 1 CO2 in gas phase. If we want to calculate or know the enthalpy change of this reaction, sometimes it's hard to measure, but we know that some other equations as individual steps, as I'm showing here. So in equation 1 is solid carbon plus water in gas phase to produce CO in gas phase and water and hydrogen in gas phase. And we know the enthalpy change of that reaction is 131.3 kilojoules per mole. For second equation, second individual steps is CO in gas phase plus water in gas phase to produce CO2 in gas phase and hydrogen in gas phase. The enthalpy change of this second step is negative 41.2 kilojoules per mole. And for the final step is methane gas phase plus water in gas phase to produce 3 hydrogen gas phase and CO in gas phase. The enthalpy change of the third step is positive 206.1 kilojoules per mole. Okay, then because the overall reaction can be split by different individual reactions, individual steps. Since we know the enthalpy change of these 3 steps, we can manipulate these 3 steps to make the chemical equation from these 3 steps to the target chemical equation as we like. And then we can also do the calculation. So there are a few things you can do. You can follow to manipulate the individual steps. So first, observe the target equation. We have as a reactant 2 carbons. So in the equation, in all of the 3 steps, there's only equation 1 that contains carbon as a reactant. Okay, contains carbon as a reactant or product, right? Carbon is only showing up here in the equation 1. However, the coefficient of equation 1 is 1 for carbon. In order to match the 2 carbon in the reaction, we can, in overall targeted reaction, we can time the coefficient, time every coefficient in equation 1 by 2. So then we can make it 2 carbons, 2 plus 2 waters to produce 2 CO and 2 water, and also delta H should be multiplied by 2. Okay, so we take care of the carbon. And then for water, we have all of the 3 reactions have water at this point. So we'll just keep it, as it is and come back to the last. Okay, then we have methane as the product. The only place we can find methane in the individual step is at equation 3. It shows up as a reactant. However, if you remember, we can flip the reactants and the product sides and put the negative sign in the delta H. We can also do that here. So we can put the negative sign in delta H3 and flip the reactant with the product. Now we can have a methane in the product side. And also for CO2, the only place it shows up in the second equation. It's also on the right side as a product, and coefficient matches, so we can use the second equation as it is. By observing the coefficient and side of the reactant and product in the targeted equation, we can first try to see if that works. As we said before, use 2 times equation 1 minus equation 3, that is put a negative sign in the equation 3, and then plus equation 2. So for the delta H, final delta H will be 2 times delta H1 plus delta H3, delta H2 minus delta H3. Okay, and let's just do the calculation of the 3 individual steps to see if the water also matches the one in the target equation. Okay, I'll just write it out here. First, 2 carbons, 2 waters, the first 2 items here, and then produce 2 COs and 2 hydrogens. Okay, we're good with equation 1. And then equation 2 is 1 CO, 1 water as reactant, and then 1 CO2 and 1 hydrogen as products. Then for equation 3, we need to minus, right? Minus the reactant, minus 1 methane and minus 1 water. Also, we need to minus the 2 products in the equation 3, minus, that is minus 3 hydrogen and CO. Okay, we don't usually like the minus sign in the chemical equation, so we can flip them around, move the group from left to right, so the negative sign will become positive. And also we can move the negative sign from the right to left, so the sign can become positive. Then we can rewrite this. All right, so this group methane and water now becomes to the right. Hydrogen and CO now becomes now show up in the left. Now we have the chemical equation with many, many items. Remember, we can also clear them up to cancel out the same amount and the same type of species on both sides. For carbon, we don't find it on the right. For water, yes, there's 1 water on the right, but on the left, okay, we have 2 places where we have water. One is here with 2 water molecules from the first equation, but from the second equation, we also have a water molecule. So we can cancel 1 water molecule out before and after reaction. I'll just do it here, okay? So then for CO, yes, we can also cancel out CO from left to right. On the left, we have 2 places show up COs. In total, we have 2 CO. On the right, we also have 2 COs, so we can cancel that. For hydrogen, on the left, we have 3 hydrogens. On the right, we have 2 hydrogen plus 1 hydrogen, that is 3 hydrogens. That cancels out perfectly. Okay, let's rewrite the equation, see what is left over. What left over is 2 carbon plus 2 water to produce 1 CO2 plus 1 methane. That's exactly our targeted equation. Also, we have the correct amount of water molecule here. Now, the manipulator of equation 1, 2, 3, all of the individual steps are correct. So we can write it out as a target equation. And to calculate the delta H, the overall enthalpy change of the reaction, use the manipulation we did, that delta H equals to 2 delta H1 plus delta H2 minus delta H3. Then we can have the value is 15.3 kilojoules per mole. Okay, since we have a positive value of delta H, again, the question comes whether it's exothermic or endothermic. When we have a positive delta H, that means the final minus initial is larger than 0. That means final is larger than the initial, right? So it means we need more heat to add on to the initial to make the final. When we need more heat for the reaction is the endothermic reaction. All right. So let's take a look at a problem that used Hess's law. When we try to solve Hess's law's problems, I recommend you to have 4 steps. Or you can use any of the steps you want, but I recommend the 4 steps. The first one is identify the target equation, whose delta H is unknown. And the second step is manipulate the known equations to match the side of chemicals and in their coefficient. And step 3 is add the manipulated equations together to get the targeted equation, and then finally calculate the delta H, based on the manipulations in step 2 and 3. So let's take a look at an example. 2 pollutants that form in automobile exhaust are CO and NO. An environmental chemist must convert these pollutants to less harmful gases through the following reaction. 1 CO in gas phase plus 1 NO in gas phase to produce 1 CO2 in gas phase and half nitrogen in gas phase with an unknown enthalpy change. So given the following information, calculate the unknown enthalpy change. It gives you 2 reactions. One is CO plus half oxygen to produce 1 CO2. The delta H equals to negative 283.0 kilojoules per mole. The second equation is 1 nitrogen plus 1 oxygen to produce 2 NO. So the delta H is 180.6 kilojoules per mole. How are we going to do that? So if we follow the 4 steps, obviously the target equation is the first one with the unknown delta H, right? Then we need to manipulate the known equations. So in order to explain it more clearly, I identify the top known equation as equation 1 and the bottom one as equation 2. Okay, so we can manipulate equation 1 and 2 to match the one in the target equation. CO is on the reactant side with a coefficient of 1. So we'll keep equation 1 as it is to match that. NO show up in the left equation on the reactant side with the coefficient of 1. So then for the second equation, I will need to decrease the coefficient of NO from 2 to 1 by divide all the coefficient by half, and also the delta H2 by half. And then we also need to flip the side of this NO. In equation 2 is on the right, we need to flip it to the left, so we need to minus equation 2. Based on our analysis, we want to do the manipulation as equation 1 minus half equation 2. Okay, so we can write it out. Equation 1 is CO plus half oxygen to produce CO2. And we need to half the equation 2. So first we have half N2 plus half oxygen to produce 1 NO, right? And we need to minus equation 2, so we need to flip them around. On the left, we need to plus 1 NO, and on the right, we need to plus half nitrogen and half oxygen here. Now we can clear this equation, cancel out the same item from left and the right. The only thing is oxygen. Okay, we cancel out oxygen from left and the right. And the final equation is CO plus NO to produce CO2 and half nitrogen, exactly the one, the targeted equation. So our manipulation is correct. So the delta H for the overall reaction is delta H1 minus half delta H2, what we did with equation 1 and 2. So plug in the numbers. The final answer is negative 373.3 kilojoules per mole. Okay, so as you may notice that all of this delta H here is not related to the standard states. It's just a delta H with no subscript, with no superscript. For the Hess's law, we can also use that to calculate the standard enthalpy change of the reaction. And also we can do that from the standard enthalpy change of the formation. Okay, so let's take a look at example. This is a reaction we discussed in the previous video as example. Titanium 4 chloride in liquid phase plus 2 water in gas phase to produce titanium oxide in solid phase and 4 hydrogen chloride in gas phase. Okay, so this is a reaction with each of the reactant as a compound, but it's measured in standard conditions, we can use standard enthalpy change of reaction to describe this reaction. For this reaction, if we write out the enthalpy change, standard enthalpy change of formation for each reactants and products, and also to match the side of the reactants and products and the coefficient of reactants and products, we can have a list of this. For titanium chloride, titanium 4 chloride, the titanium chloride is in the reactant side, so we can flip the enthalpy change, standard enthalpy change of formation or standard heat of formation. So we have the first equation. That's the negative standard heat of formation in TiCl4 liquid. For the second one, the water, we can write the standard enthalpy of formation. Also, we need to flip the left and right to make the compound side shown as a reactant side. Also, we need to do the multiply of all the coefficient by 2 to match the 2 in the target equation. So it's -2 times the standard enthalpy of formation of water in gas phase. Also, for the reactant, for the product TiO2, we can just write it out as it is. Titanium plus oxygen as TiO2 is just standard enthalpy of formation. That's the formation equation of TiO2. Also, for the hydrogen chloride, we just need to multiply the coefficient of hydrogen chloride as 4 to make the coefficient match. Okay. Then, of course, for this 2 hydrogen plus 2 chlorine to make 4 hydrogen chloride, this formation kind of derived formation equation, the enthalpy change of that reaction is 4 times the standard enthalpy change of formation of hydrogen chloride. All right, so if we add all of them together, we can cancel out the similar items on both sides. Okay, we can cancel out the titanium solid from left and the right, oxygen gas phase from left and the right, 2 hydrogen gas from left and the right, and 2 chlorine gas from left and the right. What is left over is titanium chloride in liquid plus 2 water in gas phase to produce titanium dioxide titanium 4 oxide in gas phase, in solid phase, and 4 hydrogen chloride in gas phase. That's exactly what our target equation is. So from here, we can, it's still a formation of Hess's law, and we can know that the standard enthalpy change of the reaction, that equals to the summary of the enthalpy change of products, the final ones, minus the sum of the enthalpy change, a standard enthalpy change of formation of the reactants. Also, for each standard heat formation, we need to take the coefficient into consideration. So in this case, the standard enthalpy of reaction of the targeted equation equals to the standard heat formation of the first product times 1 as its coefficient plus 4 times the standard heat of formation of its second product minus the reactant minus the standard heat of formation of the first reactant times 1 as a coefficient, and also minus the standard heat of formation of the second reactant times 2 as a coefficient. Okay, so for this equation, it's very important and something you need to know, you need to remember. The sigma means sum of. Okay, the m here means corresponding coefficient of a product. The n here means the corresponding coefficient of a reactant. And overall, this equation is the final minus the initial. So it's the product minus the reactant. Okay, so let's take a look at a related problem to calculate the standard enthalpy of reaction from standard heat of formation. Use the following to find the standard heat of formation of methanol in liquid phase. So it gives you the standard enthalpy of reaction of methanol in liquid phase plus 3/2 of oxygen in gas phase to produce 1 CO2 in gas phase and 2 water in gas phase. The standard enthalpy of reaction for that is negative 638.6 kilojoules per mole. It also gives you the standard enthalpy of formation of CO2 in gas phase as negative 393.5 kilojoules per mole, and standard heat of formation of water in gas phase as negative 241.826 kilojoules per mole. So how are we going to solve this? Okay, so for this question, it's a different way of asking. Usually the enthalpy standard heat of formation is provided, and then it's asked for the standard enthalpy change of the reaction. So in this case, it's just a different way of asking. It tests you the same equation, okay? So we have 4 different chemicals in this reaction. The first one, we need to know the standard heat of formation from this one. The second is oxygen in gas phase. If you remember, the standard state of oxygen is in the gas phase. So the standard heat of formation for oxygen elemental substance in the standard condition is 0. So the standard heat of formation of this oxygen in gas phase is 0. Then we have the standard formation of CO2 and water. So we can still plug in the equation that standard heat of reaction equals to the sum of the standard heat of formation times its coefficient of products minus the standard heat of formation of reactants times its coefficient. Okay, so plugging the values here, the standard heat of reaction equals to the products first, right? So the standard heat of formation of CO2 times 1 as a coefficient, plus standard heat of formation of water times 2 as a coefficient of water. That's the product, minus the reactant, okay, minus standard heat of formation of methanol in liquid phase, minus standard heat of formation of oxygen times 3/2 as a coefficient of oxygen. So here, the second line is the expression of the equation. Okay, so for this equation, the only item that is unknown is the standard heat formation of methanol. So then we can solve it quite easily. Plug in numbers. Remember, the heat formation of oxygen is 0, and then we can solve the standard heat formation of methanol as negative 238.552 kilojoules per mole. Okay, you can also run it off to negative 238.6 kilojoules per mole. All right, this is the end of this video, and I'll see you next time.